This is Math 5700, lecture number 38. I just want to finish up one more thing from last time, which was section 6.2. And then today we will cover section 6.3. And we're not going to do everything in that section. All right. Okay, so last time we considered the notion of independence. Random variables, which I'm going to assume are continuous. I'm not going to consider the discrete case here, although everything in the discrete case works more or less the same way. So remember what this means. It means that if we take the joint density function, not the joint density function, but the joint cumulative distribution function, then you can write that as which is just the same thing as the probability that x is less than or equal to a, y is less than or equal to b. This can be written as the product of the cumulative distribution function for x times the cumulative distribution function for y. And likewise, the density functions have the same type of relationship. That's going to be f sub x of a times f sub y of b. Okay, so that was the case of two random variables. More generally, I want to make a definition of what it means to be independent. If you have a bunch more than two random variables, let's say you have n of them, x1, x2, dot, 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 x sub n are random variables, continuous, let's say, random variables, then we'll say that they are independent if the following equation holds. If the joint distribution function, which will be denoted like this, a1 through an, which is the same thing, of course, as the probability that x1 is less than or equal to a1, x2 is less than or equal to a2, etc. So this defines a region of n-dimensional space. That's the event. And this can be written as a product of the individual probabilities. The probability x1 is less than or equal to a1 times the probability that x2 is less than or equal to a2 times the probability all the way up to the probability xn is less than or equal to an, which is the same thing as the product. I goes from 1 to n of f sub xi of a sub I. One likewise has a statement about the joint probability density functions. Similarly, f of a1 through an is the product. I goes from 1 to n of the density function from the xi evaluated ai. Okay, so this is the definition of what it means to be independent for a collection of random variables. So what I want to do today is now move to section 6.3, which is about sums of independent random variables. So why would I care about doing something like this? Well, a lot of things people do, like for example, you take a pair of dice. Each die, the outcome of a roll of each die is a random variable. And if I add them together, I get a new random variable. And we'd like to relate the distribution for the sum to the distribution of the constituents. And so I want to talk about that in the continuous case. So, and I want to talk about independent. I'm assuming that the random variables are independent here. So let's assume we have, so let's assume we have X and Y, and they're independent. And I'm only going to consider the continuous case here. So then let's consider X plus Y. That's a new random variable. And I'd like to identify the distribution function of it. What is its distribution? Okay, that's the question I want to address. So here we go. So f of X plus Y evaluated at a number of A is the probability that X plus Y is less than or equal to A. Okay, so now this probability that we're taking here is, by definition, the double integral over the region in R2 defined by X plus Y is less than or equal to A of the joint density function. So we're computing the following. So we're computing the integral of the density function over a certain region. Suppose the number A is here along the vertical axis, over the y-axis. We're looking at the region that's shaded below here. We're integrating over that region. Now, we can parameterize this as a type 2 integral, and this becomes the same thing as the integral from, so if we do that, we look at a horizontal strip, then we're integrating from minus infinity, X is going from minus infinity to that line, X plus Y equals A, and that's saying that X is A minus Y in the upper limit of integration, and then Y is going from minus infinity to infinity. So that's f of X, Y, dA. Now I'm assuming that these are independent random variables, so that would be f sub X, oops, I want to get rid of the color. Of X times f sub Y of Y, and then we would integrate with X first and then Y. Okay. Now, in order to integrate this, we see that the second function in this product has nothing to do with X. It's independent of X. So we can think of this as the integral from minus infinity to infinity of f sub Y of Y. We bring that through the integration sign, and then this is inside in minus infinity to A minus Y of f sub X of X dx. And we have to integrate with respect to Y. So this thing inside the parentheses, that's the distribution function of X evaluated at A minus Y. So in other words, we can rewrite this. I'm going to reverse the order of the terms as the minus infinity to infinity integral of f sub X evaluated at A minus Y. This is the distribution function of X evaluated at A minus Y times the density function of Y at Y dy. Okay, so this is what we got so far. This tells you the answer of what the distribution function of X plus Y is. But this is not the nicest possible formula we can write down. So let me clear the screen and rewrite this at the top, and then let's differentiate it. Okay, so this is what we got on the previous slide. Now what I'm going to do is I'm going to differentiate with respect to A. So what does that give us? Well, the left side, if we differentiate, gives the density function of the random variable x plus y evaluated at a. And what is the right side? Well, it's d by dA of this integral. Now, differentiation will commute with the integration because you can move it right through because the integral is respect to y and we're differentiating with respect to a. So this is the same as the integral from minus infinity to infinity of the derivative of this product. And now we're differentiating with respect to a. The first function involves a, but the second one doesn't. So what do you get? You get the integral from minus infinity to plus infinity of the derivative of the cumulative distribution function of x evaluated a minus y. Well, we know how to differentiate that by the chain rule. You're going to get f sub x of a minus y multiplied by the derivative of a minus y with respect to a, which is 1. And then what's left over is f sub y of y dy. So this is the answer for what the density function looks like of x plus y. And this is actually a very nice formula. So what's nice about it? Well, this here is called, usually it's called a convolution product. Of f sub x and f sub y. And it's usually denoted f sub x, there's an asterisk in the middle, star f sub y evaluated at y. So what we've just shown, if you like, is that the value of the density function at a is given by the convolution product. So it takes a sum of random variables and converts it to a convolution of functions. So this is the final answer. Okay, so what I'd like to do is do 2 examples. One example I'll work out in detail, which is for the uniform random variable, and the other I'm going to say something about the normal distribution, and then after that we will consider we will work out some problems. Okay, so let me consider the following. This is now section 6.3.1. We're going to look at the case of the sum of 2 independent uniform random variables of type 0, 1. So let's let x and y be independent of type U0, 1. Okay, so by the way, you can think of a model for this, the uniform random variable, as spinning like a spinner around a circle where the circumference of the circle has unit length, where the spinner points in a spin, that is the value of the random variable. That's the density. So now let's find the density function of x plus y. Okay, well, let's first of all recall what the density functions of x and y are. So the density function of x at a is equal to the density function of y at a, which is given by 1 if a is a number sandwiched in between 0 and 1. You can put a less than or equal to if you want to. It doesn't matter in this case, and 0 otherwise. Okay, so now what is the definition then of the of the density function of x plus y? Well, you have to integrate according to we have to form the convolution of f sub x with f sub y at a, and that will be the integral from 0, all the integration is going on between 0 and 1, because outside 0 and 1, there's nothing going on. And what do? We have to take f sub x of a minus y times times f sub y of y dy. But what is that? Well, f sub y, since y is between 0 and 1, f sub y of y is just 1. Okay, so far what do we got? We got the density function of x plus y at a is given by this formula. Now let's figure out what this integral actually is. Okay, so there are basically two cases to consider. Case 1 is when a is between 0 and 1. So I want to rewrite this integral as the integral could be rewritten as the integral from 0 to 1. Well, let me first write it again as the integral from 0 to a of f sub x of a minus y dy, plus the integral from a to 1 of f sub x of a minus y dy. Now, what happens when a is since y, we know that y is between 0 and 1, and what happens when, in this case, when a is between 0 and 1, what happens is the second integral here, this term here, what do we know about it? Well, if y is bigger than a, then a minus y is negative, and so the value of the density function is 0 from between a and 1. And then a minus y, if y is between 0 and a, is a number between 0 and 1, so this becomes a 1. So the integral becomes the same thing. I'll write it over here. The integral from 0 to a of 1 dy, which is y evaluated from 0 to a, so you're going to get an a in that case. Okay, so that's what you're going to get in that case. And what about the case where, let's look at the next case, a is between 1 and 2. By the way, a could be equal to 0 and 1, the same calculation holds. So though in that case, what you do is you can look at the integral from 0 to 1, and you rewrite it as the integral from 0 to a minus 1 of f sub x of a minus y dy, plus the integral from a minus 1 to 1 of f sub x of a minus y dy. Now in this case, if y is going from 0 to a minus 1, what happens is a minus y, since a is between 1 and 2, a minus y, since y is going from 0, is between 0 and 1. This integrand here, a minus y, is bigger than 1, so this is going to vanish as well. And this number, the integrand in the other case, is 1, and you're going to get, in this case, you can integrate, and you'll get, in this case, you can easily see that what you get is the number is y evaluated from a minus 1 to 1, and this is going to be 2 minus y. So I'm going to summarize what we got on the next slide. So what do you get? So you're going to get f of x plus y, and this is in the case of the uniform random variable, is given by a if 0 is less than or equal to a is less than or equal to 1, and 2 minus a if a is between 1 and 2, and 0 everywhere else. You can check that yourself, that you get 0 everywhere else. So what does this function look like? So it's a line of slope 1 starting at the origin. And when you hit 1, you have to use the formula 2 minus a, which is a line of slope slope minus 1 going down like this, and it's 0 elsewhere. So so this is a so-called triangular distribution. So the sum of two uniform random variables of type 0, 1 is no longer uniform. You get this triangular distribution property. Okay, so we've just computed that of the sum. Okay, so this we've just finished what I wanted to do in 6.3.1. So I want to jump now. I'm not going to cover 6.3.2. I'm going to jump to 6.3.3. Okay. So 6.3.3 is about sums of independent normal random variables. Okay, and the basic idea is that sums of independent random variables, in contrast with the uniform case, if you sum up normal random variables of any type, you'll get a normal random variable again. So this is called proposition 3.2 in the book, but I'm going to extend it a little bit. I'm going to state it in a better way. Okay, so let's choose x1 through xn, n different, n independent random variables, normal, which are normal of type n mu. So let me say it in a different way, in which xi is normal of type n mu I sigma I squared. So variance mu I, variance sigma I squared, mean mu I, expectation mu I. So then let C1 through Cn be any constants. Then we can form a new random variable, C1 x1 plus C2 x2 plus C3 x3, etc., all the way up to Cn xn. This is a linear combination of the, if you remember your linear algebra, if you had linear algebra, this would be a linear combination of the random variables x1 through xn. Okay, and the claim is, so if let's set this equal to y, then y is normal again of type n mu sigma squared, where what is mu? Mu is mu1 is C1, it's the corresponding linear combination of the mu i's. So I'll write it like this, summation Ci mu I goes from 1 to n, and sigma squared is the sum of Ci squared, sigma I squared, I goes from 1 to n. So this is the result I want to advertise. I'm not going to prove this. The book proves this, and the proof is quite tedious and boring, and I didn't feel like it was worth presenting, but I want to use this. Okay, so I want to give you some examples of this. Okay, and that'll be it for today. All right, let's start with some examples. So here's an example. Let X be normal of type N23, and Y normal of type N14, and assume X and Y are independent. So then let's find the distribution of 2x plus 3y. Okay, so we know that 2x plus 3y is normal, and we have to just figure out what the mu and the sigma squared are for it. Well, so how do we do that? Well, so this is, you can think of this as C1 is 2 and C2 is 3. So mu in this case is going to be 2 times 2 plus 3 times 3 because, oh, I didn't do that right. I'm sorry. Not 3 times 3. 2 times 2, the 2 is coming from here, and 3 times 1. So that's 4 plus 3, which is 7. And the sigma squared for this distribution is given by 2 squared times 3 plus 3 squared times 4, and that's 12 plus 36, which is 48. So 2x plus 3y is normal of type 7, 48. That's what that tells me. Okay, so now I want to do a different type of problem. So the kind of problem I want to do now is an application to the SAT exam. So it's known by the data that the math portion of SAT behaves like a normal distribution of type N529, 5732. So, and now we know the verbal portion of the SAT is N474, 63, 68. So now suppose I'd select 2 students at random. Then, and let X be the first student's SAT math score. And let Y be the second student's SAT verbal score. And the question is, what is the probability? What is the probability that that X is bigger than Y? What is the probability that the first student's math score is bigger than the second student's verbal score? We can actually answer that here. So that's the probability that X is greater than Y. Well, this is how we do it. This probability is given by the same as the probability that X minus Y is bigger than 0. Now, X and Y are normal. We know that, and we know that they're independent because we chose the 2 students randomly. So the probability x minus y is bigger than 0. This is the case of a linear combination of two normal distributions where C1 is 1 and C2 is minus 1. So, therefore, x minus y is normal of what type? Well, you can calculate its normal of type 529 minus 474, and 1 squared times 5732 plus minus 1 quantity squared times 6368. And that's normal of type 55, 12,100. I just did that calculation from before. Okay, so now we know what x minus y is, and now what I'm going to do is I'm going to convert that over here to a standard N01 distribution. So what I'm going to do is I'm going to subtract off the mean, which is 55 from x minus y, and divide by the variance, which is 12,100, to get a standard normal random variable z, and that's it being bigger, x minus y being bigger than 0 is equivalent to saying that z is bigger than 0 minus 55 over the square root of 12,100. Well, that's the same thing as the probability that z is bigger than minus a half, which is the same thing if you look at the normal curve, standard normal curve, z being bigger than negative a half, that would be here, is by symmetry z is less than, the probability that z is less than a half. And that we can look up or use a calculator. It's 0.6915 is the answer. So 69, probability is 0.6915 that the first student's math score is higher than the second student's verbal score. That's what we've just figured out. So now for my third example, the third and final example, I should say, I want to talk about an application to groceries. So it's known that so let's suppose we're looking at bags of carrots in the grocery store. If you look at a bag of carrots, there are 1 pound bags, there are 3 pound bags. But you know that if you take a 1 pound bag of carrots, it's probably not exactly 1 pound. And it seems from empirical study that if xi is the weight, I shouldn't call it xi, x is the weight of a bag of 1 pound carrots, the actual weight, then x is normally distributed. And what is the normal distribution? It's normal with mean 1.18. That means the average bag of carrots is about 1.18 pounds with variance 0.049. So, and let's let y be the weight of a 3 pound bag of carrots. So then y is, this is just due to experiment by just checking lots of carrots. It appears to be normal of type N 3.22, 0.0081. Okay, so now the question is, what's the probability that 3 randomly chosen 1 pound bags of carrots, oops, exceeds the weight of a single, randomly chosen single 3 pound bag. Well, let xi be the weight of the ith 1 pound bag that has been randomly chosen. So it's x1, we have 3 bags, so there are three of these. So what we're asking is, what's the probability that, and let's let that y is less than x1 plus x2 plus x3. Well, that's the same thing as the probability that x1 plus x2 plus x3 minus y is strictly positive. So now this random variable, x1 plus x2 plus x3 minus y, is normal. And what is its type? Well, I'll spare you the calculation. It's the same calculation we did in the previous case, similar ideas. So we're going to use the, for the mu, we're going to use this. So it's going to be normal of what type? It's going to be normal of type 0.32. 0.32. So what I've done is I've taken 1.18. Let me do the calculation. It's not hard. It's 1.18 plus 1.18 plus 1.18 minus 3.22, comma, and then in the other case it's well, 3 times 0.0049 plus 0.0081. So this is normal of type 0.32, comma 0.0028. Okay, so now we want to know what the probability is. So we need to know, we have to convert this to a standard normal random variable. So if you do that, we take, so let me do that on the next slide. Okay, so we're interested in the probability that x1 plus x2 plus x3 minus y is bigger than 0. And I'm going to convert this to a standard normal of type 0, 1. So that means I have to subtract off the mean from 0. So it's minus 0.32 and divide by the variance, which is 0.0028. And actually the square root of that in the bottom. And so that's the same thing as the probability that z is at least negative 2.12. And by the symmetry of the standard normal, this will be the same thing as the probability that z is less than or equal to 2.12. And that probability is on using a table or a calculator is 0.93830. Very likely that the sum of the 3 1-pound bags, 9.98 probability, exceeds the weight of a single 3-pound bag. So that's the third example I wanted to do, and we're at the end of the lecture today. We've finished section 6.3. 0.3, and next time we'll talk about 6.4 and 6.5.